So in this course, and even in your MEB2 class, a very important parameter that we've dealt with, or parameters, are the constant volume and the constant pressure heat capacity. And when dealing, when analyzing these chemical processes, a lot of times we had to invoke relationships between the constant pressure and constant volume heat capacity. For solids and liquids, if we assumed the system was incompressible, we said that Cp and Cv were equal. And for ideal gases, we said that Cp was just equal to Cv plus R. What we're going to do in this problem is we're actually going to, critically analyze those assumptions. And we want to quantify, how good are those assumptions, or how we even come up with those assumptions in general. All right, and so in this problem, it tells us that it's convenient to describe the PVT behavior of solids and liquids through a couple of different parameters. So there's the isobaric expansivity, which actually I would just say here, instead of alpha P, I would say call it alpha V. All right, so alpha V is equal to this, which is what we saw in the last problem. And then also isothermal compressibility, this kappa T, it's another named partial derivative, and it's equal to negative 1 over V dV dP T. Okay? All right? And so in this problem, tells us that alpha V and kappa T are very small, right? And what we want to do exactly is we want to explore, how small are they? If we're dealing with a liquid, how, if we change temperature, how much does its volume change if we keep it at constant pressure? Or if we keep the system at constant temperature, how much would its volume change if we change the pressure? Right? And to do that, to at least figure out the change in those volumes, what we want to do is we want to look at how these heat capacities change. Okay? All right, and so for part A of the problem asks us to look at derive an expression for Cp minus Cv in terms of pressure, volume, and temperature derivatives. Okay, and it also tells us that we should be able to evaluate the differences between the two if we had some sort of equation of state. Okay, all right, and so we want to figure out the difference between Cp and Cv. And as we've seen before, when we first even started discussing these different heat capacities, we know that for the constant volume heat capacity, that's related to internal energy, and the constant pressure heat capacity, that's related to enthalpy. Right? So two different types of energy functions. Okay? And so the approach we're going to take to kind of figure out the difference between Cp and Cv is we're going to kind of analyze the fundamental equations for internal energy and enthalpy in parallel. Right? And then once we have information from those two analyses, then essentially we could just subtract Cp from Cv. Right? And so I'll show you exactly what I mean. Okay? And so on the left-hand side here, so first I'll just state overall what we're doing. Let's define fundamental equations in parallel. Right, and so on the left-hand side here, I'm going to start with enthalpy. So the enthalpy fundamental equation is this. You could rederive it from your thermodynamic square. All right, and so if we take the partial derivative of enthalpy with respect to temperature at constant pressure, we know that is Cp. Right? But if we take that partial derivative with respect to the fundamental enthalpy equation up here, what we get is that Cp is equal to this. right? And we get this essentially by applying the expansion rule, right? Because you could think of it as we want to redefine enthalpy in terms of temperature and pressure, but we know the original canonical variables are entropy and pressure. Okay? And so you would apply the expansion rule in order to get this sort of statement. Alright? Alright, in any case, we have this. And on the right hand side here, we see we have a dp over dp, so that's equal to 1. Alright? Or dp, there's not dp over dp. It should be dp over dt. Okay? But we're at constant pressure. So we know, based on the properties of partial derivatives, that that should be equal to 0. And so what we get here is that our CP, our original definition that we always dealt with was this. But if we apply the calculus of thermodynamics, we now show that it's equal to this. Okay. Right, so now we have defined CP in terms of the partial derivative of entropy with respect to temperature at constant pressure. All right, we did that with enthalpy. Now let's do the same sort of analysis with internal energy. So we have du for its fundamental equation is equal to this. If we take the partial derivative of u with respect to temperature at constant volume and apply the expansion rule, we get this. This should be a t minus p dv dt at constant s. Oh wait, constant v. Oops. Okay. All right, and once again, here we have partial derivative of v dt at constant v. So that's going to be equal to 0. And so this derivative, partial derivative, is just equal to this. And we know that this here, this is just the definition of the constant volume heat capacity. So now we get Cv is equal to ds dt constant v. Okay, so now we have Cp and Cv. And what we want to do, what the problem statement asks us to do, is to find out the difference between the two. So all we're going to do is just take this and subtract off this. Right? And so what we get is this minus ds dt constant v. Okay? Alright, so by applying the calculus of thermodynamics, we have now redefined the difference between Cp and Cv in terms of these partial derivatives of entropy. But the problem statement, didn't ask for a function of entropy. It asked for something that's a function of pressure, volume, and temperature. Right? So that means we need to rewrite these things even more in order to just get them only in terms of pressure, volume, and temperature. Okay? All right, so if we take a look at these partial derivatives, we could kind of inspect their form. First we could check if maybe we could apply a Maxwell's relation to transform these. But if we look here, we have entropy and pressure, and those two things together don't make up any of the thermal conjugate pair, or any of the conjugate pairs we talked about before. So we can't really apply a Maxwell relation there. And the same thing is true for the second partial derivative. S and V don't make up a conjugate pair. Okay? So we can't apply our Maxwell's relations yet. But really, what we want to do here is, we're talking about entropy, and we want to take its partial derivative either with respect to temperature or respect to pressure or volume or something like that. Okay? All right, and so the strategy we're going to take here is what we're going to do is we're going to write out entropy as a function of temperature and also as a function of volume as well. Okay? So I'll just kind of summarize what I've been talking about. We can't use Maxwell relations yet. And so what we're going to do instead is we're going to think about entropy as a function of molar volume and temperature. Equivalently, we could think about entropy as a function of temperature and pressure. And the analysis would work the same way. But for now, we're just going to think of it in terms of, start out thinking of it in terms of volume and temperature. Okay? All right, so if we think about entropy like that, let's write its total derivative. Okay. All right, and so by writing out its total derivative, we end up with a ds dt at constant v. All right. But if we look back at our Cp minus Cv equation, we want a ds dt at constant p as well. Okay? And so if we start out by saying entropy is a function of volume and temperature, if we want that ds dt at constant p, what we want to use is that expansion rule in order to redefine it in terms of pressure. Okay? And so when we apply this expansion rule, our K is going to be volume, our L is going to be T, our Y is also going to be T, and our Z is going to be P. Okay? And so for a ds dt constant P, in the expansion rule, we first write and x. I guess I should write this. In our expansion rule template that we laid out previously, our x in this case would be entropy. Okay? All right, so if we apply the expansion rule, what we get is ds dt constant p is going to be equal to ds dv at constant t times dv dt constant p plus ds dt constant v times dt dt at constant p. Okay, so we're just following the template for the expansion rule. What we see here is we have a dt dt. That's going to be equal to 1. Okay? All right, and what we get here is we also, by doing the expansion rule, we also ended up with a ds dt at constant v. And if we look back up to when our equation for Cp minus Cv, in the end, what we want is ds dt at constant p minus ds dt at constant v. And so, as a shortcut, what we could do here is we could just subtract this and move it to the other side. ds dt constant v. And what we're left with on the right-hand side is ds dv at constant t times dv dt at constant p. So, we made progress. We now have this difference. But over here, we still have, a partial derivative in terms of entropy. But now, if we take a closer look at this partial derivative, what we see is that for these two variables, we have the thermal conjugate pair. And for these two variables, V and T, these make up the Helmholtz canonical variables. And so, if we have this format, once again, this tells us that we should take a Maxwell relation in order to redefine this partial derivative into something else. And so if we take the Maxwell relation of the Helmholtz fundamental equation, and we've done this previously, we could show that ds dv at constant t is just dp dt at constant v. Right, and so by doing this analysis, we figured out what the difference between these two partial derivatives are, and now we could plug it back into this equation. And so what we get in the end is that Cp minus Cv can be rewritten in terms of only volume, pressure, and temperature.